In this video, we'll be going over how to choose a appropriate indicator for what titration you're trying to do. So the purpose of the titration is to usually, not always, like as we saw in our buffering lab, we were just trying to see if different household chemicals could act like buffers. But usually you would want to know, or a lot of times in a titration, you want to know the concentration of the unknown titrate, or you're interested in the pH of the equivalence point because you want to find the Ka, something like that. All right, so how do you set about figuring out what indicator to use? Well, if we, just to bring some backward information into this, so since at the equivalence point are the moles of titrant equals the moles of the analyte or the titrate, then we have the molarity times the volume of the titrant equals the molarity times the volume of the analyte. So you can usually solve for this if you know the concentration of your titrant, which you would have standardized or taken a known value. And then you figure out delta V from the burette. So that would be this number here. Okay, and then you could figure out the moles of the analyte. Okay, if you weighed it, it was a solid, you weighed it, you could figure out the molar mass and so on. So when do you stop the titration? That's the thing. Okay, so what's so special about when it changes color, when you have an indicator? So you want the pH, so as this is adding OH or H plus, whatever titration you're doing, you need to know when to stop the titration so that this statement is true. So an indicator, so this is actually, I believe this is phenolphthalein, this indicator. So this is the colorless acid form of the indicator. So if you're starting off with a titration that looks like this, okay, you're doing a weak acid and it's being titrated by a strong base. So you're going to start with a low pH. Okay, so your acid will look, the indicator actually looks like this, the phenolphthalein indicator. And if you notice this, so if you notice this portion of the molecule changes when you add, when OH is added. So when OH is added, it actually will start pulling off these hydrogens on these alcohol molecules. And when those hydrogens get pulled off, the oxygen starts carrying a charge. And to stabilize the molecule, this one will carry a charge, but this one of these double bonds will actually, so one of these double bonds will actually like go from here to over here. Sorry, it'll go from here to right here and make an extra bond, okay, with the electrons so that it reduces the formal charge. Okay, when it does that, it's going to absorb light differently, okay, and then you're going to get like, okay, then you're going to get the pink form of the indicator, okay, just because it's absorbing light differently, and then the colors of light that it's reflecting back are gonna be different. So here it's not absorbing any, and all the colors of light are reflected back, so so you see white light. In here it starts absorbing oranges, yellows, blue, indigo, violet, and what's reflected back to you is like a reddish pink color. So, and that's just based off the conformation of the molecule. So it's going to absorb incoming white light differently than this one because of the spinning electrons on the resonance of these benzenes. So what's so special about that is that when this happens, there's a range where this happens, and it actually coincides when this also happens. So you actually have to choose the right indicator because based on the molecular structure of the indicator, it's going to match the pH of the equivalence point. So as you know, if you have a titration that looks like this, so if you have if you're titrating a weak base with a strong acid, then your equivalence point is going to be way down here. So if this pH is 7 around here, then your pH is going to be like way down here. So you're not going to want to choose an indicator that changes color way up here in this one. So this one will be like around 8 or 9, the pH change for phenolphthalein, or the color change. So you want a titration, or you want to choose an indicator that matches this pH of the equivalence point, the time that it changes color. So if phenolphthalein changes color around 8 or 9, then that wouldn't be a good choice for this titration, because 8 or 9 would happen, like a pH of 8 or 9 would be like way up here. Okay, so you would want a indicator that changes around like 4 or 5 for this one. Okay, and if phenolphthalein changes color 8 or 9, it's going to be clear right here. Okay, so it'll actually you'll actually start pink and then it'll go clear right here, which tells you absolutely nothing. It tells you zero information. You'll see it start pink and then it'll go clear like right here, which means nothing. You're like still in the buffer region for that titration. Okay, but for this one, it actually coincides with the stoichiometric point, so it tells you when to stop. Okay, and as you can see, you have actually a wide range, okay, where the pH changes. So for very little OH added, you have a very wide range where the pH changes. So there's actually quite a bit of room for error here because it changes color over such a wide range. So okay, so let's go into the different types of titrations that you'll see. Okay, so this is kind of summarizing the points I was saying on the previous slide. Okay, and then I have it summarized in these on these titration curves also. So when titrating an acid, you want it on the lower end of the color change. If you're titrating a base, so if you're titrating an acid, meaning that's just because your titration curve will look something like that. Okay, so pH, this is volume of the titrant, usually OH. Okay, and so you want it, just because over time the pH is slowly increasing, then you want the pH to happen on the lower end of the color change. So you want it to happen here. This is the lower end of the color change. And the AP exam doesn't really require you to be this specific, so I'm going to summarize this in a second. Okay, so if you're titrating a base, so like a weak base strong acid titration, which looks kind of like this, then you're like a pH of 7 is around, the neutrals around there. Okay, your equivalence points are gonna be a little bit less. Okay, and it says you want the color change to be about on the upper end. That's because over time your pH is decreasing, so you want to catch it when it starts to decrease. You don't want to miss that range. Okay, so this is about +1 of the color change. Okay, and you may or may not need to know it that specific in like the state or UC schools. I mean, you may have to know it that specific, sorry, but on the AP exam, I haven't really seen them require you to know it this specific. So let me summarize the concept here. So generally speaking, you want the pK of the indicator, which is when it changes color. So the pH of the color change. Okay, so i.e., we could reword this, the pH of the color change. I can't spell color. The pH of the color change to be plus or minus 1 of the pH of the equivalence point. Okay, and so what that means is you'll need to know what species is present at the equivalence point. So for this goes right along with what I was saying earlier. Is for this your pH is greater than 7, so you want the indicator to change color around that time. This one, your pH is much less than 7, or it could be slightly less than 7, so you want the color change to happen at that point. So the correct indicator to use for this titration is probably going to be way different than the correct indicator to use for this one, because they're different molecules, as I was going over in the previous slide. Look at that again. So the molecular structure for all the indicators, there's a big list of indicators in the book. The molecular structure, those are all, individual molecules. They have these completely different conformities that they do, and so they change the way that they absorb light at much different pHs depending on the molecule. So, but this is the concept right here. So let me just box this in red. This right here. So this is really kind of a good summary, I think, is right there. Okay. So by by saying species, I kind of like make it generic, so you have to know, what kind of titration you're doing. So let's go and look at different titration curves. Oh, so this is the list. So this is from the Zoomdall. I believe that even the ninth, even the newer editions probably have this too. But these are all the different indicators. As you can see, these all change colors at lots of different pH ranges. So these ones that are like over 7 and 8-ish, like around here. So these are probably all good for, or this is for like a really, really strong acid. This one right here, a alizarin yellow R. This one might be used for like a really strong acid, meaning wait a second. I'm not thinking about this correctly. So this would be your base. So your base would actually be strong. So these would be for like really, really weak acids. Like really weak. Okay. And the reason I'm saying that is because you see our pH right here of this color change is happening around 11, like 10 and a half or so. So your equivalence point pH would have to be like 10 and a half or so. So that means something like HCN, that Ka is like 10 to the negative 10th, meaning its Kb is like 10 to the negative 4th, which is pretty strong base. So like Cn minus is a pretty strong. It's a weak base, but it's pretty strong. Okay, and these would be for like the average acids would be like these guys right here. Okay, and then for like really, really weak bases, meaning the conjugate is really strong, then you might use something like that. And these would be more for like your average type bases. They're the bulk of the bases will be used. Any one of these will be okay. So let's look at the different titration curves, and this also helps us summarize it visually. So this goes to describe visually what I was describing before. Is here's a weak acid with strong base. Okay, so a good indicator for that would be phenolphthalein, what we've been using a lot this year. And as you see, the color change happens between 8.3 and right around 10 or so is when it starts changing pink. Okay, so methyl red would be a horrible choice because you'll miss the equivalence point. So it'll change color like during the buffer region. Okay, so if you chose this incorrectly, you would stop your titration and go, oh, look, I'm done. I found the equivalence point. Okay, but, if you followed it with a pH meter, you'll see that this was like a poor choice for this type of titration. So what I boxed earlier in red, that's what I mean by you have to know what species you have. Okay, so like for like acetic acid, okay, then at the equivalence point, you're going to have CH3COO, the acetate ion, okay, which is why you have a high pH right there. Okay, so this would be a bad choice, something like that, methyl red. Okay, and if we look at a weak base and strong acid titration, now if we use phenolphthalein for that one, we'll miss the equivalence point. So this is a poor choice for this titration. Okay, and then we want to use something like methyl red for that titration because this catches the stoichiometric point or the equivalence point right here. Okay, so this would be something like NH. Like if you did this titration, so if you did like NH3 plus a strong base, okay, at the equivalence point, these two guys are wiped out, and then you form 100% of the conjugate, okay, which is an acid, okay, which is why your pH is lower than 7, and that would be a good. I would have to know the volumes and concentrations and find the pH, but this is probably a proper choice for this titration. Okay, and here's our third titration. If you do a strong acid and strong base, you could see this one's interesting because, if we think of our earth table here, and we're doing, at these points here, you start off with a strong acid and you're adding some base, and let's say you got 10 millimole, 1 millimole, okay. Then this guy gets wiped out, and then you end up forming then you end up with 9 millimole left over. Okay, so that'd be right here. Then you have like 8 millimole left over, 7 millimole, 5, 4, 6, 3, 2, 1. Okay, then all of a sudden you have no millimole left over, so which would be like right here. Okay, this would be like 9.9 and 10. Okay, and then so this gets wiped out, but you only have 0.1 left over. So basically, your strong acid's getting diluted, sort of. Okay, so then you'd be like right here. Okay, and then your equivalence point is this massive range right here because there is no conjugate. Okay, and at the equivalence point is 7. So you have this huge spike in pH from here to here. So you could actually use phenolphthalein or methyl red for a strong acid, strong base titration because of this huge range of pH change. So normally the pH can be plus or minus 1 of the color change. But for strong acid, strong base, look at this range. You have 10, anywhere from 10 to 4 is good. Okay, so if the pKa of the indicator, which is when it changes color, is around 7, so you could actually do plus or minus like almost 3 of that number. Okay, and you could catch the equivalence point with either. So you have a huge range of choices you can use for this type of titration. All right, so let's look at a couple problems. I'm calling this target practice. So it says how much titrant would be required to reach the equivalence point, halfway point, and what indicator would you use for each of the following titrations? Okay, so here's my first problem, and I'm going to do the second one. In the year turn on this video, there's 4 of these that are similar. So refer back to these notes to see how to do it. Okay, so I use round numbers, and this is what they're going to do on like multiple choice on the AP exam if one of these kinds of questions shows up. So because you won't have a calculator, so you'll need to know how to do this in your head. So you have 100 and 0.1 HF hydrofluoric acid, and it's being titrated by 0.2 molar NaOH. As you see, this right here is double the concentration of this. So if you have 100 of this, if this is twice as concentrated as your acid, you will only need half as much of this. So you need half as much NaOH because it's twice as concentrated as the HF. Okay, and we could do this with a stoichiometric relationship. So just to prove this point. So you could go, and I'm going to leave this in millimole. Okay, so my volumes cancel. Okay, and then it's in this reaction, it's 1-to-1. Okay, nothing's diproduct or anything like that. So it's 1 mole of OH is reacting for each mole of HF. Okay, and then I go, so I want to know the volume, so I invert the molarity to use it as a conversion factor. So I write 1 liter over 0.2. My answer is going to be in ml because I didn't convert right here. I left it in millimole. So 1 mole of OH. Okay, I type this in my calculator, and I get, so I'm going to get, what do I get? 10 over 0.2 or 50. Okay, which is what I got intuitively just by looking at this. So I noticed it was twice as concentrated, so it's going to take twice as much. Okay, so this of NaOH. Okay, so that's the answer to A. That's to get to the equivalence point. To get to the halfway point, so to get to the halfway point, it should take half of that. So it'll take 25 ml to get to the halfway point. And it says, what indicator would you use? So to answer C, I need to find the pH at the equivalence point. Okay, so I know it's a weak acid and strong base, but as you know, all the weak acids differ in their Ka. So we can't just say phenolphthalein and move on. So I'm going to calculate this. I need to know what I need to know here is on my ice table. So I'm going to have I have HF, and it's being converted to its conjugate. Okay, so it's being converted to F minus. Okay, and so at the equivalence point, this is gone and this is gone. So I need to know the moles of this, and I need to know the total volume. Okay, So my moles of this is going to equal the moles of this and this at the equivalence point, the initial moles of this before it reacted, because all of it is being consumed and going over there. So my F minus at the equivalence point, this is the number I need for my ice table, is going to be 0.10 molar times 100 milliliters. Okay, so that's my moles. That's my moles of F minus. Okay, and I'm going to divide that by the total volume, and I figured out that it took 50 ml NaOH to get to the equivalence point. Okay, and I started with 100 mils of the HF, so I go 100 plus 50, so that's where I get 150. Okay, and this is the total volume. And check your guys' titration cheat sheets if you are struggling with this, how I'm doing this. So this is the V total at the equivalence point. Okay, and so this is the number I need for my ice table. I did this beforehand, and I got 0.067 molar. Okay, if I set up my ice table, I get this. I'm going to have the F minus. Sorry, I changed slides there. So I'm going to have F minus interacting with water at the equivalence point here. Okay, so I'm going to create barely any of that because it's just creating it based on equilibrium. So I don't have a significant amount of that. So, and I'm going to go 0.067. Okay, so I run it through my ice table. Okay, I think you guys know how to do that by now. And I get, I'm going to need the KB for this. So I plug it into my ice table. Okay, and I'm going to wind up with this. So I'm going to wind up with OH equals square root of KB times F minus. Okay, this is the result from my ice table. And I'm going to get, for this, I get 0.067 times, which was the concentration of F minus, times 1.5 times 10 to the negative 11th, which is the KB. Okay, square root that number, and I get 6.00. Okay, subtract from 14, and my pH is 8.00 is the pH. So if I go back to a couple slides ago, okay, I want the pH to be, I want one where the pH changes around 8. Okay, so this one's a good choice right here. The phenol red and nitrophenol is good. You could also use cresylphthalene and phenolphthalein. You could use any 4 of these. So those are all acceptable responses. So you generally want it to do it on the lower end. So cresylphthalene or phenolphthalein are, but like I said, you do it plus or minus 1 of the color change. Okay, so I'm gonna say cresylphthalene or phenolphthalein for this one. Okay, so you could use cresylphthalene or phenolphthalein for that titration. Okay, so I'm gonna do this one pretty fast just to save time. So I see that this is what I'm titrating it with is half the concentration. Okay, so my titrant this time, or the analyte, I'm sorry, the titrate or the analyte is double the concentration of the titrant this time. So since this is half the concentration, I'm going to need twice as what I have here. So I'm going to need 100 milliliters of the HNO3 to reach the equivalence point to get equal moles with the NH3. Okay, and to get halfway, I'm going to need half of that. So I need 50 ml of the HNO3 for the halfway point. Okay, and so for the total volume, so to run this through my ice table, the species present at the equivalence point is going to be NH4+. Okay, it's going to act like an acid. Okay, and so I need to know this concentration, which is going to be 50 ml times 0.1 divided by the total volume, which is 150, because it took 100 and I had 50 of it there originally. Okay, and so this number is 0.033 molar, 0.033 molar of the NH4. Okay, so this is 0, this is 0, minus x plus x plus x. Okay, use the assumption rule, all that stuff. Okay, your Ka is going to be H plus. This is the stuff I kind of ran out of space on the previous one from writing all this out. Okay, NH4. All right, now plug in our values here. So the x, or H plus, is going to be the square root of, because this is going to be x times x, and it's going to be over 0.033. The square root of the Ka times NH4 plus. Okay, and let me just write that number for you here. I have, sorry, I keep changing slides. My hand hits the next button. So I get a pH of 5.37 for the pH. And if I go back to my indicators, so I need the color change. So the pH of the equivalence point is around 5.37. So I need the color change to be plus or minus 1 of that number. So this is probably fine, brome cresol green or methyl red. So either of those is probably fine. Even this one, Erichrome black, is probably fine. Okay, so I'll just write methyl red or brome cresol green for that. Okay, so I want to use brome cresol green or methyl red for this titration. Okay, now finally for the your turn. Okay, so it's just like what I was doing. I tried to use round numbers here so that you could kind of do the earth table in your head. And if you get stuck for how to do the calculations on the equivalence line, I know I went a little fast on the previous slide. Use the cheat sheet that we did on titration. So it should have everything you need, all the steps you need that I was doing. All right, so see what you guys come up with on that.